The purpose of this video is to discuss the three most and simplest forms of ordinary differential equations that arise in pretty much many disciplines of engineering, whether you're a civil engineer, whether you're an electrical engineer, mechanical engineer. If you know the solutions to these three differential equations, for the most part, that's going to go a long way in helping you study various subjects. So let's see what they are. All right. So we're going to talk about the three simplest. ODEs is my abbreviation for ordinary differential equations. So the first one is obviously very simple. So dy dx equals a constant. And in this case, I can integrate this and write down the solution as cx plus c1. So y equals cx plus c1 would be the solution to this differential equation. If you kind of ignore this constant c1, then the solution to this differential equation is y equals cx. And the reason, or just a recap, the c1 comes about, typically it's prescribed through an initial condition. So this would be dy dx equals a constant. So typically this problem will have an initial condition that is specified. And the word initial is kind of connotes time, but here the way to think about it is I am going to prescribe the value of y at x equals 0 as some constant. Let's call that constant c1. Okay. And so if I plug in x equals 0 into this equation, you can see y would be equal to c1. That's the initial condition. So the prescription of c1, the initial condition, will solve this problem completely. Right, and so this is the simplest differential equation. So when dy dx is a constant, and this is probably quite obvious to you, but it's amazing in how many situations you come across this equation. So it's very important for us to kind of have a very thorough understanding of the solution. The second one, so the second common differential equation that arises in many engineering problems, let's write it this way: dy dt equals minus lambda times y. All right. One way to think about the solution of this differential equation is, of course, to go back to a diff-EQ class, and you can figure that out. That's not the way I'm going to look at it. Instead, I'm going to pose the following question: what function of y do you know that, when differentiated with respect to the independent variable time, gives me back the same function? Notice on the right hand side I got y, but also throws in a coefficient minus lambda in front of it, right? So what function do we know, when differentiated, gives me back the same function with a negative sign if I ignore the coefficient lambda, right? The answer is if I have an exponential with a negative time, right? So if I differentiate this with respect to t, I'm going to get exponential of minus t, and then a minus sign pops out. All I need to do is put in a lambda here, and this will be the solution to this equation. And the most general form of the solution to this equation will be y of t equals some constant y0 times exponential of minus lambda t. And the role y0 plays is similar to the role c1 played in the previous problem. It is based on the initial condition. So I can prescribe, for instance, along with this differential equation, I can insist that y of 0 equals y0. All right. So when time t equals 0, as you can see from the solution, the function y of 0 becomes y0 because the exponential of 0 over here is equal to unity. All right, so this is the general form of the solution for the second type of differential equation, dy dt equals minus lambda y, right? So let's summarize. In the case of 1, the solution is simply y as a function of x is essentially a straight line. In the case of the second situation, y as a function of t, the solution starts out at some value y0 at time t equals 0, and then it decreases exponentially, right? So this is exponential of minus lambda t, right? And starts out at y0. Another comment I want to make is to relate this solution here to the principle of dimensional consistency that we've talked about earlier. So the dimensions of y have to equal the dimensions of the right hand side, which I can break it up as the dimension of y naught times the dimension of this exponential term. All right, and the dimension of y naught is clearly the same as the dimensions of y. So, and the exponential has to be a dimensionless quantity. Not only that, the argument of the exponential, which is lambda t, also has to be a dimensionless quantity. So in other words, the dimensions of minus lambda t, remember that's what you read these square parentheses as, negative lambda t dimensions equals 1. So it means the dimensions of lambda have to equal 1 over t. And so often 1 over lambda, which obviously will have the dimensions of time, will be called a time constant in the problem. All right, so 1 over lambda might be called a time constant, and sometimes this is given a symbol tau. So tau, which is equal to 1 over lambda, is called a time constant. So in other words, the solution may be written as y equals y0 exponential of minus t over tau. Okay, and so this is the second most important differential equation. The third one is actually a second order differential equation. So let's write that down. D squared y dx squared equals lambda squared y with a negative sign. Okay. And again, the way to approach this problem is to think about what function do you know which, when differentiated twice, right, because I'm differentiating y twice, gives me back the original function, which is y, except for a negative sign if I ignore this lambda, right? And the one we know from is from trigonometry, sines and cosines. When I differentiate them twice, I get back the sines and cosines, but for a negative sign, right? So and this being a second order differential equation in general has two solutions, and so the solution for this equation can be written down really by inspection as c1 cosine lambda x plus c2 sine lambda x. All right, so this is the general solution to this differential equation, and what will determine c1 and c2 are the initial conditions. So you may be given in the problem y at time or at position x equals 0 is something, and we may also be given another quantity dy dx at some x equals 0 is equal to another constant. Let's give that a symbol c, right? So if I know these two, then I can figure out what c1 and c2 are in this equation, right? So let's summarize. We got three types of differential equation. Dy dx is a constant. Then we got dy dx equals minus lambda y, and then d squared y dx squared equals minus lambda squared y, right? So if you know the solution to these three problems, you can wade through a lot of engineering. You can survive in engineering and in many different disciplines, right? So the solution to this problem is simply a straight line. The solution to this problem, which I can write as the constant x plus yet another constant c1. The solution to this problem is simply an exponential function, which I'll leave it that way. And the solution to this problem involves cosine lambda x and sine lambda x, right? So if I know these three, I can make a lot of progress in engineering problems.